Hello everyone. Today we are going to present two different papers on artificial intelligence. The first one will be learning real-time A-star path planner for unmanned air vehicle target sensing. The other one is KNN LRT A-star simple subgoaling for real-time search. So first, let's look at the first paper, that is learning real-time A-star path planner for unmanned air vehicle target sensing. So these are some of the content topics that we'll be discussing today. And for the introduction. So as we know, autonomous mobile devices use the pathfinding algorithm to plan the path it has to travel. So in this case, in this paper, in this case for autonomous mobile vehicles, the pathfinding is easy. So if we apply the same concept to fixed wing aircrafts, it is difficult to find the path. So that is because there are a lot of limitations, some of which is the turning radius, which is minimum, and sensing the ground targets through aerial sensing. And we are not just considering these turning radius, but if the targets are placed far apart, then it is easy to find the path. But if they are placed closer to each other, then it can't be used. The traditional pathfinding algorithm can't be used. So the problem here is for this paper, it is to develop a pathfinding or path planning for targets that are closely spaced, which also considers the turning radius of the aircraft. And what is the objective here to achieve this? So it is to get to the path that has a minimum to see all the targets. The path that is minimum to find all the targets that are closely spaced. Then to find the solution to this problem, we have three challenges that are listed here. That is coupling between path segments, utilization of the sensor footprint, and determining of the viewing order of the targets. So let us just see how the standard approach to find an optimal path from one point to another is. So as you can see in the first diagram, if targets are placed widely in relation to the turning capacity of the vehicle, then we can plan to find the optimal position from starting until we reach all the targets. If the targets are placed closely, then the coupling between the path segments because of the turning limitation can lead to not so optimal solution. This negative effect can be illustrated, as I said, in figure 1A, where we start to find the optimal solution from the starting point, as you can see here. So because of these, we are going in curves here. And the head of the aircraft, after the first target, it has to take a turn to see the second target. Because of the position of the head is poorly positioned, it takes a longer path to reach the second target. And similarly, from second target to third target, to view the third target, it takes a longer path again, because the head position of the aircraft is it's in the wrong, it's poorly positioned. So the segments 2 and 3 are also optimal when we consider the starting point and the end sign point of the target. So this kind of path is called suboptimal path, where we do have an optimal path between two different targets, but the overall target, like the overall algorithm final path, is not an optimal path. Then in figure 1B, as we can see, it is a multi-target optimal path. So we see that the path from the starting to the first target is long. But when the vehicle reaches target 1, it has a clear view, like what is the next target in its way, and what path and which path it has to take to view all the targets and give a minimum path length. So let's go to the next slide. And here, this is another example. So most of the pathfinding approaches have paths that pass directly above the targets. But these approaches have a lot of restrictions. So the sensor footprint of the sensors used are of significant size. So because of the pathfinder restriction that the target has to be viewed when the vehicle flies over, the range and the flexibility of the sensors are not used. So if we have a sensor that has significant footprint size, then using it would help increase the complexity of pathfinding. So as you can see, because the sensors are not utilized, are not being utilized in its full capacity. So once from the starting, once it comes here, it has to take a turn, a big curve to reach the second point. But by the time it's reached the second target, it has already traversed the third target once. So it'll have to go to the third target again. So this rotation is what we can avoid if we use the uh, full capacity of the sensors that are fit in the aircraft. So the final challenge also of viewing the targets in close proximity is the order in which the targets are viewed. So also, since we have limitations on the turning radius along with finding the viewing order, we will consider only constant altitude, constant velocity flights with a downward viewing sensors. So let's look at the effective path planning. So the effective path planning approach to view the closely spaced targets are, we have to plan in such a way that we have the optimal or near optimal paths between the targets to overcome the coupling effect between the path segments, and then use the sensor footprints fully so that we can eliminate the need to fly directly over the target, and then finding the viewing order of the targets to get to the minimum length path. Some of the approaches that this paper has gone through are, first, we're using the learning real-time A-star search, where we can find the optimal path while using the effective path planning approaches. The only drawback here is that this search is only applicable when we know the start and the end target. But here we are focusing on the scenario where we don't know the end target. And then we have the Dubin's traveling salesperson's problem. So it is proof that for a given path, from the start to the finish, there will be turns followed by straight segments, which is again followed by turns. So where the turns are of minimum radius. On this approach, Salva et al. Uses his approach to find suboptimal tour with the worst case length, which gives us the worst case length. But Richard et al. Uses this approach to develop a hybrid A-star automation approach. And then there's Yang and Kapila, who uses Dubin's traveling salesperson problem and vector calculus to find the optimal path. But for this, the order of the target has to be visited, should be specified before the path calculation. So that's again a drawback here. And then we see Cavani and Hedricks, they work closely on the closely spaced target problem. So the approach they used was to group the targets and view the groups to achieve effective viewing of the targets. Then there is McAllen and Beard use the potential force-based method for path planning. In this approach, the path is considered as a chain with segments that are repulsed by the threads and each other as well to form a path which is flyable. But this can't be used for real-time path planning as it is very slow. And we have the Frezzoli et al. Who worked on randomizing probability path search, which is also called probability road mapping. In this algorithm, it considers configurations and plans path to these configurations. Using this, a roadmap can be constructed for the target. This search main idea is to keep searching until they reach one single path after the search has gone an infinite loop. Then we have the rapidly exploring random trees approach, where they explore the one loop control input sequence where we start from the initial target and move until the goal target is reached. Then Lavelle and Kufner did a variation to this to improve the search speed. Then Saunders et al. Used a 3D waypoint path and used it for simulations and flight tests. Finally, we have the mixed integer linear programming approach, So that has been used for development of aircraft applications. It is used to find collision-free paths from start target to the end target, but it needs extra software to solve the optimization problem. Now that we have the approaches and the effective planning set, let's go to the next topic, that is discrete step path. So discrete step path planning algorithm helps helps use the effective planning approach. So to achieve this, we treat each segment in a discrete path of length ds. This length is with the this length is with respect to turns made at a minimum turn radius or a straight line. So minimum turning radius is RT, which helps the vehicle achieve maximum heading change at each step. Then the step size is a fixed value. So the number of steps in a given path is calculated using n, which is p of n by d5, and where pn is the normalized path length. Now we assign the left, right, and the straight primitive with which we create the tree here. So to all the flyable paths. Now A is the parent node and C are the group of children or the set of child nodes. Then T is the set of known targets and S is the record of the target sensed by the node's ancestors. Then the path tree here has a depth of 3. The number of nodes a tree grows exponentially with the depth of the tree. Also, there are limitations set on the depth of the tree due to the computer memory limit. So due to this limitation, it is recommended to construct a fixed length tree that uses the computer memory available. So for desktops, it's usually the tree depth can be from 30 to 50. Now, as we can see, we have the second diagram. So the position and the altitude of the vehicle are shown using the standard aircraft notation here. So the configuration of the vehicle at a given node is given by P, X, Y, phi, where X and Y are the inertial position and phi is the heading of the vehicle measured from north. And the DI is the vector of the ith target. Now, the configuration of a child node is generated by calculating the change in the heading and position in relation to the parent configuration. So the equation for the child configurations in here, PL, PS, and PR are shown here. So targets are detected by the vehicle whenever they are within the sensor footprint of the vehicle. The presented algorithm can incorporate sensor footprints of any size and shape. So here the sensor footprints is rectangular with X sensor as 1.2 of RT and Y sensor as 0.5 RT. And its center is situated directly beneath the vehicle. Here the discrete path, so in this case, the discrete path here is 2-dimensional, but this can also be incorporated in 3 dimension. So now Shumaila will take it from here.
Hello everyone, this is Shumaila, and here I will explain you about LRTA start research algorithm. So this is an online algorithm. LRTA means learning real-time A-star algorithm. So in which robot works. So it means that a robot has no knowledge of its surrounds and it just knows where it wants to go. That means goal. Thus it goes around and discover its surroundings, because online algorithms are all about sense and move. The robot first senses the environment and updates its knowledge into a table and then moves. Then again it senses updates again, and so on. So this algorithm works like this. It is a real-time algorithm which determines branch of a defined path tree best achieves the required path planning objectives. And this LRTA star algorithm can be used to solve any sort of world like grids, trees, directed graphs, etc. So here you can see the algorithm is mentioned. So I will tell you how does it work. So each node has a heuristic estimate, that is H. So each node the uh, calculates the remaining trip distance, that is FC, and the formula of FC is KC plus HC, where FC is the projected remaining trip, and KC is the heuristic estimate. KC is the cost of shifting, and HC is the child's heuristic estimate. So every time the current node's heuristic value is updated. So the search proceeds down the tree until all the objectives are met or the path grows longer than the current optimal path, at which time the search returns to the root node. The heuristic value for the current node is updated with a better estimate of the distance to the target at each step of the search. Next slide, please. So in this algorithm, we will discuss about initial heuristic. Here, with the help of this figure, the LRTA star search primary criteria is that the HI should be less than or equal to H star I, and it is always true for any node I. So this is the heuristic value in any node. So the explanation is quite straightforward. If a node on the ideal path overestimates the distance to the target, the search may never reach that goal and never reach the next node, and hence never identify the best path. So admissible heuristics are heuristics that conservatively estimate the truth path length, and determining proper initial values of these heuristics is critical to the LRTA star search success. Next slide, please. Now, the terminating condition. So we can see in the diagram, there are two diagrams. First diagram shows the path plan using LRTA star algorithm, and the second diagram shows the path plan using NI-LRTA star algorithm. So mainly, first of all, the strategy utilized in the tree search has a direct impact on the tree search speed and path length performance. So on one extreme, the search continues until the heuristic change is 0, ensuring that the shortest path is identified, but at the cost of a substantial amount of time. Here, the non-improving LRTA star, that is NI-LRTA star algorithm. So it is basically a tree search algorithm with the ending condition. So this algorithm terminates when the path length does not improve, but LRTA star algorithm terminates when the heuristic estimate does not increase. So the more iterations required, the better the path lengths will be, but at the expense of higher running time, because the optimal path is often located soon, and most of the search time is spent validating that it is actually the optimum. This terminating condition is successful. Next slide, please. So in the branch terminal, node's heuristic value is always less than or equal to its actual path length. So the current node is terminated by moving its children and setting its heuristic value to infinite when the presently examined branch grows longer than the currently optimal path, and the search is restarted at the root node. If all nodes children have infinite heuristic values, the node is a dead end and can be terminated similarly. The heuristic value of a node is always less than or equal to the actual path length, as we all know it. Next slide, please. Path tree size. So in this topic, we will discuss how we calculate the path tree size. So the size of the path tree is a key issue while searching it. The size of the tree grows very quickly as the step size lowers, making investigating the tree a time-consuming operation. The whole path tree is 3 to power d in size, with where d is a denoting the number of levels. Because of the enormous number of nodes that must be evaluated, the search will be slow and memory space to keep the visited nodes will be limited. So in this figure, there are root nodes, left node, right node, and a straight node. So figure shows an example tree search structure with a two-step look back. A more efficient strategy, on the other hand, is to use some other path planning method before using LRTS start research to generate a flyable path that achieves the intended objectives, not optimally. Next slide, please. Step size selection is the key to a successful LRTA start research that is small enough to best approximate the global optimum while not making the tree too vast to search quickly. The findings reveal that when choosing a step size, a trade-off must be made between speed and path length performance, and that bigger step sizes considerably enhance the algorithm's running time with only a minimal increase in path lengths. Next slide, please. So here we see testing and comparison between LRTA star and NILRTA star. Using step sizes less than 0.2 radians does not considerably reduce the path lengths produced by the algorithm, according to the algorithm testing. So here we have two diagrams which shows the validation. So first one is with pinpoint sensor footprint LRTA star closely approximates optimal path obtained by brute force global search, and the second one is to utilizes large sensor footprints to produce a shorter path, and it is around 33% shorter path. Next slide, please. Path length. So we have the diagrams. In the diagram, blue color shows the LRTA star, and the red color shows the mean distance for NILRTA star algorithm. So the path lengths for the two algorithms at various step sizes shown in figure. So over the spectrum of step sizes, the mean path length increases by about 90%, demonstrating that the smaller step sizes are preferable. The picture also demonstrates that the NILRTA star algorithms, means path length performance, is comparable to that of the LRA star algorithm. So it is little bit equal, we could say, and it means that NILRTA star algorithm's path lengths are longer than the LRTA star algorithm. So it is clearly mentioned here with this diagram. Next slide, please. It's running time. So in this, there are two figures again showing the findings of LRTA star and NILRTA star algorithms at various step sizes with the average overall running times in terms of nodes visited and for both the algorithms. So the test results also reveal that the NILRTA star method is substantially faster than the LRTA star algorithm and performs similarly in terms of path length. So with the help of this diagram, it is clearly mentioned that the NILRTA star is a little bit faster comparable to LRTA star. Next slide, please. Differing number of targets. So in the first figure, there are running times versus number of targets, and the second diagram, path lengths versus number of targets. So it is mentioned. First figure shows that the running times of both the LRTA star and NILRTA star algorithms grow as the number of target increases. We can see in the diagram. The LRTA star algorithm visits an average of around 5.5 million nodes for 8 targets compared to an average of 200,000 nodes for the NILRTA star methods. Uh, so next slide, please. Now we come to the conclusion. Whatever I explained. So we have discussed about two algorithms, the LRTA star and NILRTA star tree search algorithm. So these are presented to locate the branch from a discrete step path tree that best accomplishes a set of goals. So the LRTA star algorithm will always generate the shortest path, but it will take longer to run. The NILRTA star algorithm successfully trades off some path length performance in exchange of significantly shorter running times. Both the algorithms in this way, we could say, give feasible solutions to multiple closely spaced target sensing problem, as well as the flexibility to incorporate several goals and information. Thank you. Now Monica will continue.
Hello, this is Monica Madineni. I would like to tell you about KNN LRTA star simple subgoaling for real-time search. Next slide. Yeah, in this paper, I would like to give you a brief introduction, subgoal database construction, runtime search, and the empirical evaluation. Next slide. Yeah, first of all, I would like to give you a brief introduction about this. A series of computer games in which artificial intelligence is in charge of the experts are supported by continuous heuristic hunt computations. These continuous pursuit computations, on the other hand, use a different computation, the LRTA star, which tries to eliminate advancing by picking subgoals suitably. A memory requesting pre-calculation stage during which its subgoals removes the primary constraint to deploying best in class continuous hunt methods in computer games. While detecting 9% more incorrect arrangements, calculation utilized a fraction of the memory used by the LRTA. Next slide. Introduction. Agents in these video games that are controlled by artificial intelligence, and the algorithm should be in real time to scale up to big maps and large number of agents at the same time. Searching for heuristic search algorithms is a prevalent problem in video games. This challenge is approached in fundamentally different way with the real-time search. This computes only a first few actions for the agent to do rather than computing a complete. Real-time heuristic search algorithms adjust their heuristics to handle the issue. Because they have not been frequently used for pathfinding, they have a tendency to heuristic functions and relax the problem. The first heuristic search algorithm, the LRTA star, operates in real time and evaluates a state during the pre-processing step. The new approach creates a database of subgoals instead of evaluating a map and create a click-based abstraction. We scan the database during the problem solving process to come up with the subgoal for LRTA star. Pathfinding on video game maps will be used to explain concept and assess. The new method of LRTA star can be used for a variety of real-time search activities. Here, the grid map is converted to graph and then abstract to create a single abstract state for each click of original state. After the abstraction, ground level is created. The representatives are indicated by white circles and the ground level states are abstracted to different states by wearing colors. Next slide, please. Yeah, sub-goal database construction. The LRTA star builds the database by first abstracting the map. This considers all pairings of abstract states after partitioning a map into regions and path between the ground level representatives of the two abstract states that is optimal. The path from the start representative is then traced and the ground level state where the path subgoal for the pair of abstract states is marked as shown in the figure 1. V is the number of abstract states at the abstraction level, while V is the number of ground level states. The LRTA code is complex. So a myopic LRTA star is essentially hill climbing with the addition of a Bellman updating rule for heuristic. Simple hill climbing is required to reach the agent. The best subgoal of goal is the farthest state along an optimal path from a starting point by basic calculations as shown in the figure 2. Next slide, please. Yeah, the offline database building element of KNN LRTA star is built using the resulting algorithm in figure 3. N random pairs of ground level states that are reachable from each other and are at least 2 moves apart. We execute A star for each pair to calculate an optimal path P between the pair states S dash start and S dash goal and a specified number of subgoals n. For I greater than or equals to 3, then we have to generate n random pairs and n. We use simple hill climbing with the heuristic derived with regard to Si to each of if each Si is reachable from S start. Subgoal for start and goal is characterized as the farthest state on the way P, which is at hill climbing reachable from start. From the figure 4, heuristic distance between agent situation S start S goal and the closest database record S dash start, S dash goal, S dash sub goal are shown by double-ended arrows. Next slide. Runtime search. Here, the agent state and the goal will not be stored in a subgoals database. Exact aim, but will have to generalize from records. This method is used to pick subgoals with the K set to 1 for simplicity. When an agent transitions from state as start to state as goal, it searches the subgoal database for the closest similar record. The agent sets the subgoal is just subgoal from the database record and uses the normal LRTA star to get here. Notice how we employ hill climbing reachability tests to limit all hill climbing checks as the map grows in size. Here we have some issues that need to be addressed. First, the global goal may be accessible by hill climbing from the agent current state, and the agent may choose a subgoal that will lead it away from the goal. We handle this by determining if the global aim has been met. If that's the case, we will skip the subgoal selection entirely and focus just on the overall goal. It is not always true that the agent's real state start is hill climbing reachable. As a result of LRTA star, learning process can be proactive by expanding the amount of records in database is an attempt to increase record in database. The possibility of cycles in the third issue. We solve this problem by keeping a taboo list of the subgoals that the agent uses on a daily basis. As a result, no subgoal can be chosen more than once. If the record is on the other side of an impediment, the agent will have to spend a lot of time working its way around it. When we have exhausted the second most comparable record in the database, the agent switches to the global target. Next slide. I would like to say the properties. One second. Yeah. KNN LRTA star either performs LRTA or computes a subgoal at any moment. In the worst case scenario, the agent will stop computing similarity and the hill climbing reachability for all records in database. KNN LRTA is a complete in the sense that it discovers its objectives in a finite amount of time. If the map is finite and the goal is in the same linked component as the agent's initial state. As a result, the agent will always achieve its sub-goal and each sub-goal can be employed once. The agent states is achievable from the sub-goal and the agent sets out the achieve. Because the number of sub-goals is limited, the agent will, in the worst case scenario, visit each one before running LRTA star to the global goal. The memory complexity of KNN LRTA star asymptotically is O of n. O of V for LRTS heuristic and for the taboo list T, it's O of n. The memory usage is limited to O of n plus V. Next slide. Empirical evaluation. These are the 8 maps that we use for empirical evaluation. We performed 128 distinct pathfinding problem instances on each map with the start and goal location set at random but confirmed so that the best solution was found. We offer an average of 1024 pathfinding searches for each data point. Next slide. Here, the suboptimality of paths taken by agents controlled either by the LRTA star or optimum ones as shown in the figure. The suboptimality as a function of database size is depicted on the left subplot. The database size is expressed as a percentage of the map size. Observe that KNN LRTA star subgoal databases are often substantially smaller than their DLRTA counterparts. Suboptimality is depicted in the right subplot as a function of the number of states expanded every move. Because of its reachability test, KNN LRTA star is more expensive each move. We may conclude that KNN LRTA star outperforms GLRTA while utilizing significantly less RAM for its subgoal databases. This advantages comes at the cost of slightly longer pre-computation durations for creating sub-goal databases and a more sophisticated runtime module. Next slide. Conclusion. I would like to conclude this by reducing the memory restrictions of the LRTA, a current state-of-the-art real-time search algorithms, a high-performance real-time search algorithm appropriate for pathfinding in video games has been developed. The new method known as KNN LRTA star provides runtime real-time performance while demanding many of the same characteristics as AI algorithms used in video games. Next slide. Future scope. The LRTA star runtime performance has been improved even further. First, rather than choosing the start goal combinations at random, our similarity metric on the other hand does. Instead of obstacle-aware similarity metric should be select a valid map state closest to the weightage average of the K subgoals. By matching subgoal recommendations for numerous database records K greater than 1 and selecting a single nearest neighbor K equals to 1. Next slide. That's it. Thank you.